Okay, here is example 2. And we again have a cantilever, and the cantilever looks very similar to the example 1. Just apart from the concentrated load W, we have another concentrated load P at the free end. Then the supporting roller, not at A, is at B. So the first step, of course, will replace the redundant restraint roller B with reaction force By. Right, then we split the structure into simpler parts. So here, how many parts do you think we need to split it? Depending on the number of loadings, right? We have a concentrated load W, we have 2 concentrated loads, that is P and By. So we need to at least split it into 3 simpler parts. Right, so 1 cantilever subjected to distributed load W, 1 subjected to concentrated load P, another subjected to concentrated load By. Right, as shown here, we will have these 3 beams, right? Beam 1, beam 2, and beam 3. Right, then we just determine the deformation at point B. Right, in these 3 cases, then we consider the compatibility condition in step 4. Okay, so we have done step 1 and step 2. So we start from step 3. Okay, in step 3, we have 3 beams that we need to deal with. Let's look at beam 1. Okay, the beam 1 here. Oh, it's a cantilever subjected to concentrated load W through BC. As we analyzed before several times, here we can calculate the maximum delta B, and here we call it delta B1, okay, at point B. And again, we know that the AB will keep straight, so we can calculate the slope at the point B, then use a triangle to solve the deflection at point A. But that is useless for us in this example, since we're only caring about point B. We're not calculating deflection at point A. So that triangle analysis will be useless in this example. So we only calculate delta B1. Okay, here the delta B1 can be calculated using an equation in our table. I hope you still remember that. We'll just use the equation 29, right? The 29 here. Okay, it's just a cantilever beam subjected to a distributed load. Right? We just use this equation to calculate delta B1. Well, here over delta B1 equals WL to the 4th over 8EI. That will be W's 82 kips per feet, right? So we got 82 by, so what is the L here in this case? Will this L be L1, L2, or L1 plus L2? Here, of course, in this case, our L equals L2. That is 2 yard. Right? 2 yard, as shown here. 2 yards equals 6 feet. Right, so we need to use 6 here. Right? 6 to the 4th over 8 times 43,000. It keeps square foot. Then you will get the result here will be 0.308 foot. And here we just used equation 29. Then let's look at beam 2. the beam 2 is here, then it's a cantilever subjected to a concentrated load at the free end A, that is P equals 110 kips. Then we are calculating the deflection at the point B. Let's call it delta B2. Right. So here at this point, just to calculate delta B2, we need to use the equation in this table, since we will just select it. I believe that will be equation 21, because this is a cantilever beam subjected to a concentrated load at the free end, and we're calculating the deflection at a point X. At a point X. So in our case, the X equals what? X here equals L2, or 6 feet, and the L equals L1 plus L2, that is 9 feet, right? So our equation 21, that is P x squared over 6EI times 3L minus X. So that will be 110 by 6 square over 6 times 43,000 times 3 times 9 minus 6. Okay, the result will be 0.322 feet. And here, this is our equation 21. Then our beam 3. The beam 3 is here. This is the cantilever beam subjected to a concentrated load. Again, here, this obviously we will know that if you add this load By at point B, the AB will always keep straight, and we can use a triangle to solve the deflection at point A, but that is useless in our case. Okay, so you just simply consider, just remove this part, right? Remove this part. Only consider BC, right? It's a cantilever BC subjected to a concentrated load By at point B, the free end. Okay, so we'll just use equation 20. Okay, in this case. Here our delta B3. Let's call it delta B3. Okay, delta B3 equals PL cube over 3EI. That is P equals By times, so what is the L in this case? Again, here this L equals L2, right? That is 6 feet. So we use here the L is 6 cube over 3 times 43,000. So that is By over 597.2 feet. And here this is our equation 20. Okay, then there will be our step 4. Right, so in step 4 we will analyze the compatibility. Right, the compatibility at point B. What is the compatibility condition? Okay, here just before we do this analysis, we need to identify the directions and the signs of these deflections, right? So here in the first component, the delta B1, obviously the delta B1 will be a downward, it's a downward deflection. And delta B2 is another downward deflection. But the component delta B3 is a upward deflection. So these three components have two different signs, right? So just to write the compatibility condition, we just have delta B1 plus delta B2 minus delta B3. That is 0. Right? That is our overall compatibility condition. So you have delta B1 plus delta B2 minus delta B3. That equals 0. So we have 0.308 plus 0.322 minus by over 597.2 equals 0. And the by can be solved in this way. That is 376 kips. Okay, that's it.